This is an example on how to convert an expression from a normalized form as a sum of products or a product of sum to a canonical form. It is to a sum of minterms or to a product of minterms. To do so, we use basically the identities and the axioms, of Boolean algebra. So basically, to convert the sum of product into sum of minterms, what I need to do is to add in every term here the missing literals. For example, this term doesn't have the B and C literals in this function. This term has all the literals, so this is actually already a minterm. And this term here lacks the A literal. So to add the missing literals, what we do is that we multiply the terms by 1. And this one, we build the one using the complement theorem like this, using the sum of a variable and its complement. Okay, so this way, this will be A and B plus B complemented, because the B literal is missing, and I could also add C plus C complement because the C literal is also missing. The next term I leave as is, and in the third term I add the A literal by doing the same. Okay, all these some terms are equal to 1, so it doesn't change the expression because I multiply or I do the n operation with 1. But the good thing is that if now we apply the distributivity property here, this one here, we will obtain all the possibilities. I will apply the distributivity property slowly in 2 steps. This one will be AB plus AB complemented. Okay, C plus C complemented plus AB complemented C, and in this case is AB complemented C plus A complemented B complemented C. Okay, so I apply it again, so this would be all this one times C, A, B, C, plus A, B complemented C, this one plus, so I actually plus A, B, C complemented, this one times this one plus A, B complemented C complement. Okay, so actually we don't need these parentheses here, so we can delete them. And now I add the rest of the terms that I have already operated. I B complemented C plus A complemented B complemented C. Now, this is a sum of minterms, but it's not still a canonical form because we should not repeat the minterms. If I can eliminate repeated minterms, because we can use the theorem that says that x plus x is equal to x. So if I repeat any term, I can leave just one copy of the term. So this is minterm ABC, AB complemented C, this is not repeated, not repeated. This one is already here, so I can eliminate this copy. This is the same minterm actually, and this is a complemented. Okay, so finally this is A B, C, plus AB complemented C, plus AB, C complemented, plus AB complemented, C complemented, plus A complemented, B complemented C. Now if we want to write it in the compact form, I just have to identify the midterms with their numeric value. So if I assume that the sorting of variables is A, comma B, comma C, okay, this will be the midterm that is 1 for this code 111. So this is midterm number 7. Okay, this will be midterm 101. So this is midterm number 5. In the same way, this is 110, midterm number 6. This is midterm 100, number 4. And 001, this is midterm number 1. So in the compact expression, it will be the sum of midterms 1, 4, 5, 6, 7. 1, 4, 5, 6, 7. Okay. In a product of sums, we do it in the same way, but now what we need to do is to add literals to the sum terms. So in this case, here I have to include the C literal, and here I have to include the B literal. To do so, I apply the dual property. In this case, we apply this one. So that way I can add a term like this to the sum terms with the missing literals without changing the sum, without changing the OR operation. So it will be A, B complemented C. This is already a max term, so we don't have to change anything. Here I have A plus B, so I add C, C complemented, which this is a 0, okay, so nothing changes. And I add the B here. This will be A plus B, B complemented, plus C. And now it comes the difficult part, because we have to apply the distributivity property of the sum with respect to the product. So here we have A plus B complemented plus C. And now here I add C first, A plus B plus C, and then I do the product, and I have the same part here, but now I add C complemented. A plus B plus C complemented. Okay, so just by applying the distributivity property, but now of the sum with respect to the product, which is the dual that we don't have in real numbers, for example. So it's not, we are not that familiar with that property. Now for the last one, it is the same. I have A and C, so I add B, but I'll keep the variables, the literals, sorted in alphabetical order, okay? And now I add B complemented. Now that's it. Now we check that we are not repeating terms. If I repeat any term, we can apply the theorem that says that x and x is equal to x. For example, here, this is AB complemented C, AB complemented C, so it can be eliminated. And ABC, ABC, this can be eliminated as well. Okay. Now, AB complemented, we have these three max terms: A plus B complemented plus C, A plus B plus C, A plus B plus C complemented. If we want to write it in the compact form as the product of max terms, I have to find which max term index they are. I again assume that the sorting of variables is like this. So this is the max term, that is 0 for the combination 0, 1, 0. So this is max term 2. This max term is 0 when variables are 0, 0, and 0. So this is max term 0. And to make this max term equal to 0, I have to put the 0, 0, 1. So this is max term 1. So this expression is the product of max terms 0, 1, 2. Okay? Now we can check if we have done it correctly, because both expressions are not the same actually. So we cannot check it. So that's it. Thank you.